Today we want to solve an ordinary differential equation using a finite difference approximation. In here we can see some of the equations for the finite difference approximation using forward, backward, central for the first derivative, and this is for the second derivative. Here we have a case of a temperature distribution of a rod that is defined by this equation. We will not discuss about this equation or how to generate this equation. We here only want to solve this equation using a finite difference approximation. Discretization using a finite difference approximation. Here we have an equation about temperature distribution at several points of this length of the rod. So there are three conditions. At the first, when the temperature at the end is equal to the temperature of air, and then the second condition, if the end is isolated, and then the third condition, if there is a convection or heat convection at the end of the rod, so there's heat transfer here. For the first problem or for the first condition, we have discussed at the class how to make or how to discretization or discreting this equation 6.1. In here, we can transform the equation 6.1 to a finite difference approximation here for the second derivative. So we have equation 6.2, and then we can simplify the equation and make the equation 6.4. So the constants here, we change it to alpha. We have the general equation for this problem, and then we can see at several points or several I how is the equation became. So at the first, when the I is 0, or at the very left or the rod or the first point of the rod, we have a temperature that is equal to the temperature of the wall, which is 400 centigrade. And at the I of 1, we can transform the equation 6.4 to equation 6.5, and then next until the I equal to end or at the end of the rod. So the temperature is exact same like the temperature of the air. From this equation, we know that we have a pattern like this, a diagonally pattern that at the diagonal position, we have -2 plus alpha for the variable. So we have matrix of A like this. We transform the equations to matrices A power B equal to C. What we want to solve or we want to know are the values of t1, t2 to the tn minus 1. So we can simply using a matrix to solve it in Matlab. But before that, we have to conditioning the the values of the matrices. So we have to change to the page of the Matlab. Okay, at first, we have to name our folder 1, and then clear the page or the common window, and then we have to add the nonce variables. There are K, which is the heat conductivity, and H, that is the coefficient of heat transfer. D is the diameter of rod. L, length of rod. Sorry, there's a mistake. And then this is for the first condition. And then C of the wall, 400. Temperature of the wall. And C of the air for udara, 30. Air temperature. And we have a condition which T at the end is the same with the temperature of the air. After we add the knowns, we can generate matrices. But first, we have to set how much is the grid points. And here, we make an example for 101 n points, and we add we calculate the dx. Dx is the step size or the length of each x or each grid points. We can calculate this with the length of the road. Sorry, the length of the road here is 50, should be 50. And then we can calculate the dx by using L divided by n minus 1. N is the grid points, so n minus 1 are the total interval or total delta x or dx that we have. So remember this equation because this will be used for any other cases. And then we add a matrix of or length of x using a linspace 0 to L with n points. So from 0 to L at many n points. So and then we can add the constants here before adding the equation. Alpha, which is 4 cos h, and then per k d and dx squared. We add alpha at first here because we want to make a loop for the matrices, for the inside of the matrices or the loop for matrices A, B, and C. First, for A, we make a matrices with a size of n minus 2 cross n minus 2. So there are n minus 2 rows and n minus 2 columns. How do we know that the size of the matrix is gonna be n minus 2 and n minus 2? So we have a condition for the first condition. We have known the n, the 0 point or the first point. So we can reduce or we can remove the first point, which is the first point is when the T or temperature is the same like the temperature of the wall. And then we also can remove the n at the end. So, and at the end we have known, or I can just add here, we have known T0 and Tn. So we can reduce the size of the matrix for only n minus 2 rows and n minus 2 columns. And for the result, we also add n minus 2 column, sorry, n minus 2 rows with one column, with only one column. Minus, we have this pattern. We have this pattern at every points except for the row 1 and for the n row. We have pattern that we have c minus alpha tu minus alpha tu. So we can just add here mean minus alpha and tu. So in our matrices, at in the matrix A, we have a different values at the first row and the n row. In other rows, it will be like this: 1 minus 2 and 1. 1 minus 2 plus alpha and 1. And then here we can see also 1 minus 2 plus alpha and 1. But we have different condition at the first and the end rows. At the first row, we have started from minus 2 plus alpha and then 1. And at the end of the row, we have started to 1 and minus 2 plus alpha. And we have different conditions also for the C. At the first row, we have minus alpha tu mean C W, and then at the end, we have minus tu alpha plus 1. So different from other results for C. So we can add these conditions at first. Matrix matrix of A at row 2 and the column at the first row and the first column. Minus 2 plus alpha, and at the first row, the second column, 1. And the first row of C minus alpha, Tu minus T double. Yeah. Okay, for the other variables of the other rows and columns, we can add or we can add the values using 4 for j so the columns for the column of 1 to n minus 2, so n minus 2 at the end of the column, and for I or row of 2 so n minus 3, because we don't want to any error for this, so we just add I from 2 to n minus 3, because if we use n minus 2, so we will have an error or not a diagonal position if the column is the same like the row. The value of A in this position will be minus 2 plus alpha. This is the diagonal value of the matrix, diagonal constant. Else, if row is if the column is I plus 1, so the value of A will be 1. Else, if the column is row minus 1, the value of A will be 1. And we end this loop, and also we haven't at the end of the value of A and C, the end of the row. So at the end of the row, first at the end row and end minus 1, we have 1 value of A, and then at the row of the end and the end column, we have minus 2 plus alpha. So to make a minimum of errors, or if we want to see if our M file is good enough, or not any error, there aren't any errors, so we can try to run at several points. So we have to save this first, please remember how to solve the M file properly. Don't use a space, don't use some symbols. If you want to use some space, just use an underscore like this. I'm gonna make this to case one. When I run this M file, there's no error, so I can move forward. For the Cn, for the value of the very end of the row, we have minus alpha plus 1 Tu. Please remember these values are similar with our matrices. So we have to determine the matrices first, and then we can make this matrices or this condition in the Matlab. Okay, to calculate the T or the temperature distribution, we can simply using matrix um, syntax here. So solving the temperature distribution of we if we want to only know the temperature at several points or at every point, we can just using this and run. So here we can see the value of B at n minus 1 cross n minus 1 matrix. These values are not the values from T wall and Tn. So this is we excluding the T wall and Tn here. So if we want to know the exact temperature from the T wall to the T end, we can displaying the result, display the result with defining the T is matrix of T wall, temperature of the wall, and then we add values of B here in the middle, and then we will end the matrix or the result using temperature of air. So we have at the 30 at the end of the road, and then we have 400 at the first or the initial temperature, the very left temperature of the road, same like the temperature of the wall. From here, we have we can also display the plot of the temperature distribution using syntax plot xt. Plot xt, we can wait to the plot generated now. So here we have the temperature distribution. But if you want to make a more eye-catching result or want to make it for a table like it'll displaying in a table or a better result, not a better result but just a better display, I mean a better display for the result, we can make a table of result using printf results and the new rule, and then printf to make the table. Just add this, and then next for the position for x, and then the temperature, and then table border, and then sorry, we have to use n to make a new line to enter the table, and then printf for the values. The values here I add for the x is 4.0, but you can use any numbers here to learn more what's the meaning of this number. And then 8.4f and a new line, and we have to add what's this 4.1f for. We want to add the condition for x from 1, sorry, there's, and T or temperature. So we add this these values. We will add these values from X and T. And we add the border here. So using this fprintf, we can see the result for a better display. I'm sorry, there I forgot to add the new line. So after we run, we have this good display for the table or for the temperature distribution. You can try with changing this and this to know how is the effect of different values of n and different different values of the difference between x and t.